All right, that should be good to go. How's it going?
Good, how are you?
I'm doing all right. Okay, continuous probability was last time. How are you going now?
Right. I think the like probability density function is pretty cool.
Hmm.
Because use my like previous knowledge,
Hmm.
integration and stuff.
Yeah, precisely. It's practically just calculus again. Like there's nothing actually different beyond like the phrasing of the question, but fundamentally all it's ever telling you to do is solve a definite integral or solve a variable within the definite integral. Yeah. Cool. Okay, so if that's all fair enough, was there anything from that chapter section you want to revise any deeper, or do you want to move on?
Uh, from the whole of continuous?
Say again?
From the whole of chapter 15, you're saying?
Yeah, yeah,
Okay, let me flip through it because I've got the book here with me as well.
yeah. There were two main things. One was solving probabilities using it, and the other was solving the statistics, like mean, standard deviation, median, variance.
I mean, those like were pretty okay because they have like formulas for
Yeah,
them.
yeah.
Um, probabilities for that. Oh no, it wasn't too bad to be honest. Like, because it was just inputting like the terminals into an integral.
Yeah, precisely. It was figuring out
Equating
what
to one,
terminals. Yeah,
or equating to one. It just
yeah, correct.
yeah, them.
You're either putting in the terminals and then just solving what it is, or putting the terminals and making it equal something, usually 1, but if you're doing like your um, percentiles, for instance, you equate it to whatever the percentile is.
Yeah, pretty alright.
Cool. Okay, with that in mind, normal distribution is up next. Normal distribution is actually a kind of continuous probability. So all of the rules that are applicable to continuous probability are also applicable to the normal distribution. You'd more commonly understand this as a bell curve. A lot of real-world things follow the normal distribution, or at least approximately normally distributed. For instance, grades of mathematics scores will be normally distributed. A lot of people will be set about this average study score of 30, and then depending on how high you get, becomes increasingly more and more difficult to get that next study score increase, which is why going from, for instance, 49 to 50 is such a major increase versus going from 30 to 31. It's because it's non-linear. Each individual study score increase becomes vanishingly more difficult to achieve because you're getting more and more standard deviations separated from the mean. This thing does have a particular equation. In the book, you'll need to understand that equation and use it, which implies that maybe in a SAC that'll be applicable. However, in the actual exam, I've never needed to use this. Sometimes under very weird circumstances, like maybe these, for instance, you'd want to graph or get a picture of it in your CAS, and this will be the sort of thing you do. You'll notice the standard deviation terms as the sigma, the mean as mu, and then, well, you just got your x, and E is just Euler's number. Pi, of course, pi. Yeah, it's still just some function, f of x. And you can kind of see just based off of what the terms are and where they are that, you've got this x minus mean. Whenever you have x minus a value, that's usually some sort of horizontal translation. And sure enough, if we were to look at like where the mean is in our picture, it's just going to be the center of wherever the bell curve is. So kind of like how you would set a turning point for the quadratic, where the horizontal location of that is, rather, you would do x minus that number. And if you look at where the standard deviation terms are located, those are located in what are effectively dilation factor spots. You get a dilation along the x and a dilation along the y, or I guess kind of a dilation, the inverse of a dilation along the y here, because it's in a denominator. That's less important to understand that they're either affecting the x or the y. More important to understand that they're just stretching the graph. And that should make sense because standard deviation is a measure of spread, how far spread out a probability distribution is, whether it's normal or otherwise. And so what ends up being the case is when you have a small standard deviation, you have quite a concentrated little curve going on there. It's quite tall, but really narrow. Whereas if you have a large standard deviation, it becomes a lot wider. And in order to maintain the area of 1 under these curves, if you make it wider, it must therefore be shorter. These kinds of questions show up in the textbook. I think I've actually ripped this exact photo from the textbook, the Cambridge one anyway. And they'll get you to effectively try to figure out what has a different standard deviation, which one has a different mean, or what are they in relation to each other. But okay, one of the things we can use a lot with the normal distribution is the symmetry. So I didn't really touch on this, but maybe I'll do it now. They're always symmetrical about the mean. And each number of standard deviations either side of it is going to correspond with an approximate probability that comes with it. So when it comes to solving probabilities in the normal distribution, there's two main ways you go about it, depending on if you're, for one, tech-free or two, tech-active. Tech-active, what you're doing is simply using the normal CDF. That's really all it is. Works basically the exact same way as the binomial PDF. You need a lower and an upper. But instead of finding n and p, you're looking for the mean and standard deviation. That's really all it is. CAS is super easy in that regard. The tech-free version, they'll still give you the mean and standard deviation, but you now have to use the approximate probabilities. So what we typically understand from the normal distribution is these three key domains of, domains of probability. They're called confidence intervals. You've got the 68, 95, and 99% rules, which correspond to plus minus 1, plus minus 2, and plus minus 3 standard deviations, separated from the mean specifically.
Yeah.
This is one left and one right. There's your approximate 68%. This is two left and two right. There's your 95%. And then, well, of course, 99% as well. The one you'll use most often is going to be the 95% rule, specifically when calculating confidence intervals. However, you'll be using number 3 is quite rare. Usually you're using these two and just sort of playing with them together until you get the target probability you're looking for. How does that look? Well, fundamentally, you'll be given the mean and standard deviation, and you'll be told to figure out what probability you're looking for. So you draw this out by hand relatively easily. Usually what you do is you draw out the mean first, and then just draw a little bell curve centered at that. If you want, you can do tick intervals of 15 either side. So 115 here would be your one standard deviation. But usually you just write the number that's actually given to you, and you rationalize it in terms of how many standard deviations am I to the left or right. So in this case, mean of 100, the value we're looking to be above is 115. That is effectively one standard deviation to the right. So we're looking for this probability, everything right of that. My preferred way of doing things is to pretty much always start by saying it's 50-50 either side. So that always gives me at least one half of the entire thing separated. And then all I do is I look at which approximate probability I have. So if it's one standard deviation, which it is, I'm using the 68% rule, which means 68 is either side, so therefore 34% is just this side. I've got 50 all the way over here, I've got 34 all the way here. To make sure everything adds up to 1, well, that means 16% is going to be what's left over. Cool?
Yep.
Okay. So that's how you solve it tech-free. The other kind of question that gets asked a decent amount is not necessarily finding probabilities, but finding a specific x value, something along the domain. Usually I'll call it k or maybe even z when we get into the standard normal distribution. The question will be worded something to the effect of, you have this mean, you have this standard deviation, and you'll be given a target probability. So if it says 80% or below, that would be x less than some value k is equal to 80%. And in this case, we're trying to find out what the k actually is. What is that score that's left over? Tech active, you're just using the inverse normal. For our CAS, the TI Inspire, just make sure that what you put in the area is the percentage that is left of the value you're trying to find. This one's already pointing left. It's a less than sign, so it's going to the left of the distribution. So we would happily just put 0.8 in there. However, if this was x greater than k is 0.8 or 80%, what you put in here is now going to be 0.2. It always has to be to the left. The just for the recording, the other everyone who has the Casio, you can actually choose what tail you use. It'll give you an option of left, right, or center. You'll pick left if it's pointing left. You'll pick right if it's pointing right. Center is its own little thing. You usually use those for stuff where is it? Where you are looking equidistant from the mean. That's what center helps with, but I've very rarely seen that be required. Yeah, okay, that's that. Tech free we'll look at when we start looking at standard normal distribution, because you need an equation from that, which we'll be doing right now, actually, I guess. Maybe before that, anything in there worth clarifying further?
Could you just go over that inverse normal thing again?
Yeah. Where did it go? Inverse normal. So the goal here is to effectively find these numbers, right? Like your x values on the x-axis. And you'll be given a target probability, and you'll be told the probability is either left or right of the value you're trying to find. So the wording would be, a normally distributed random variable has a mean of this, a standard deviation of that. Find the value of variable such that 80% of scores are below, above, whatever the terminology is. First step is taking all this information and putting it into a probability equation. You pretty much do this for literally all the probability. You take the word and then write something like this before you go any further. The key information here is going to be the actual action statement there. Find the value of k for which 80% of scores are below. Cool. This is what that looks like, mathematically speaking. The background information then helps us get there. So, fair enough on how we created this?
Yes.
Cool. When you're trying to solve a number on the x-axis rather than a probability, you're using inverse normal. This was also true of binomial, although I remember it being a bit of a pain to work with. That, or I just didn't have the patience to actually figure out how inverse binom worked. But there were other ways we got around that. So realistically, when you're doing normal distribution, there's only two key tech active things you're doing. If you're trying to find a probability, you're doing just regular normal CDF. If you're doing anything else, pretty much anything else, you're using the inverse normal, because that gives you an x coordinate. The syntax is you need the probability, specifically the probability to the left of the value you're looking for, and you need the mean and standard deviation, which is common to all normal distribution type questions. So the only point I was trying to make here was the TI Inspire doesn't have an option of saying, are you pointing left or are you pointing right? It always thinks you're talking about percentiles, which percentiles always look left. So when you have x less than k, you have some value k over here. Everything less than k would be pointing left. Right of k, or greater than k, would be pointing to the right. The thing that you put in the CAS is always the probability on the left. So if I said x greater than k was 20%, the equivalent of that would be to say x less than k is 80%. You just flip that over if necessary. Clear enough?
Yeah.
Cool. Introducing the standard normal distribution, which fundamentally isn't actually really any different to the regular normal distribution at all. It just has a mean of 0 and a standard deviation of 1 always. It is standardized, essentially. We typically think of the x-axis now in terms of z values or z scores rather than x values. So whenever you see a question that refers to normal distribution or standard normal distribution, you'll see that anything with capital X is going to be the regular normal, and anything with capital Z is going to be the standard normal. So when you have a statement like this, you'll now know, cool, that's the normal distribution thing, and that's the standard normal distribution thing, and there's some equivalence between them because there's an equal sign there. This is important to remember because when you're using the inverse normal in the CAS, it can double up helping you find Z values as well, because all you do is you plug in the mean of 0 and the standard deviation of 1. In fact, that's the default in the CAS. If you literally just type it up now and get to the inverse normal, it'll default the values as 0 and 1, respectively. When you're doing it tech-free or even tech-active, you still want this equation. This is effectively a transformation from Z to X, or vice versa, depending on what information you already had. Z is equal to X minus mean over standard deviation. So as long as you have 3 of those values, you can now find the 4th. This is how any equation works. If you have everything but 1 of the values, you can find the one that's left over. Typically, when you get questions about standard normal distribution, it's never really in isolation. You're pretty much always playing with the regular normal distribution as well, basically always using this equation or some version of this equation, like so. In this case, we're told the regular normal distribution has a mean of 6 and a variance of 4, and we want to find b such that this series of equations is true. So because there is a way to get from the regular normal distribution to the standard normal distribution, or vice versa, you can always draw an equivalence between them. So right now I have a probability in terms of x, which is equal to a probability in terms of z. That's what I'm told. And my goal is to figure out this value here, b. So if we think about like what it looks like in terms of x greater than 7, 7 is just some x-axis value. So when I see z less than b, that's also an x-axis value, but it's just written as a z instead of an x, because it's standard normal. So what we're effectively saying is, okay, what is the z equivalent of this spot, more or less, or at least of this probability thing? One of the first things you want to do is make sure both inequalities are actually facing in the right way, or the same way, I should say. Because what I kind of said there was a little bit incorrect. It's not just what is 7 in terms of z, and the reason why is because the inequalities are pointing in different directions. Like for instance, x greater than 7 is pointing that way, but z less than b, well, a less than would be pointing in the other direction. And so one of the things you want to do first is flip whatever inequality you know the most about. So in this one, we actually have the value rather than just some b. It's easier to do the one that you know the most about. Flip that into the same direction. And the way you do that is you start with your mean and variance, so I guess you want to convert that to standard deviation. Plot that in the distribution, so you can see it's centered at 6. And so x greater than 7, well, since 7 is 1 more than 6, then to flip it to the other direction and get an equivalent probability using that symmetry, you just go 1 to the left instead. So 6 minus 1 gets you to 5. And so for that reason, everything left of here is the same as everything right of here. Cool.
Yep.
Okay. Now that we have the inequalities in the right direction, we have probability of x less than 5 is now equal to probability of z less than b. Now we can draw a direct equivalence between 5 and b. 5 is the x value, and b is the z value, which we're going to solve. Mean and standard deviation, well, we knew mean was 6, and the standard deviation is just the square root of variance. We have all the terms on this side, so whatever z value you get left with is that value that was labeled b here. Quick sanity check on that. Make sure if it's on the left, you do in fact get a negative, and if it's on the right, you do in fact get a positive, because you got to remember that the standard normal distribution is always centered at 0. So if it's left, it's negative. If it's right, it's positive. Fair enough.
Yep.
The z equation can be used to solve literally any of these terms in here, because you'll often have enough information to find the other three. You're doing the exact same stuff though. I've made it a bit more complicated here by chucking a 1 minus in there. You can attack this however you like. You can make both of these say 1 minus and then just look at the inequalities that way, or you can do what I did, which was just kill the 1 minus altogether. So they'll now again point in the right direction, but there's less complexity in there. So first I did, what's the probability of z greater than 1.5? Well, that's going to be here-ish on the standard normal. And so 1 minus that is pointing that direction, or in other words, left. So you just flip that to being z less than 1.5. Inequalities in the right direction. Here's my x, here's my z. Bang, bang. That's those two. Mean is solved already, we were told up here. And we had to find the standard deviation instead.
Just to clarify with the graphs, even though it has a mean of 250, it's like it looks like it's centered around 0, so
Yep.
I just
So the thing that I chose to work on was the z distribution. I was messing with this one. And so when I'm drawing my curve, I'm making it a standard normal, which is always centered at 0, and standard deviation 1.
Okay. Well, the one that was above this one, the graph before this, was that also a standard normal?
No, because I was
because
working
like-
with the x stuff. So if I wanted to play with z, I would draw the z version of this instead.
Yeah.
If I want to play with x, I'd draw the x version.
Yeah, right.
Yeah, both works totally fine. Like you could draw this one up and then do a flip 1 minus. It's purely a personal preference. And that's those. So I know I wrote normal PDF in there. I mean, it does work, but I've never seen a question where they've asked for the probability of a specific outcome. Yeah, so you're pretty much only ever using CDF and inverse normal. CDF for probabilities, inverse normal for effectively everything else. And as for tech-free, you're always using the 68, 95, and 99% approximations for solving those probabilities, or even solving those Z-related stuff, because you're still, I guess you're not really doing too much of that for Z. You're just sort of thinking in terms of standard deviations rather than the actual probabilities are associated with. Anyway, those are the two main things there. Anything worth focusing on specifically, or just top to bottom?
Probably just top to bottom.
Yeah, let's do it. Distribution. What are they got going on here? Actually, yeah, no, this is a decent one to start with because it's a bit conceptual. Question 1, you've got two different normal distributions. One of them has, well, they have different means, different standard deviations. This is the relationship between them. And it tells us to sketch both. If you want to sketch it to get a picture of it, by all means, but if you can answer it without drawing it, that's also cool. If the first one has a smaller mean than the second one, what does that say about the relationship between the graphs?
If one of the means would be larger, then that means the standard deviation should be smaller because when the standard deviation is larger, then the graph has to become shorter to accommodate for the height.
So that statement is true, but the initial premise is not quite, because the mean is actually an x value, not a y value. So yes, it's going to shrink in terms of its height, but the mean will still be in the center, no matter how tall or short it is. So close. When we're thinking about specifically mean, it's effectively telling you where the center of the graph is. So if one has a smaller mean than the other, it just means it's more left than the other one is. Smaller number means more left, bigger number means more right. That's all it means for the mean. It's effectively a horizontal translation term. And then standard deviation, you mentioned a bit about that already. How about purely based on comparing one to the other? What does it mean if you have a smaller standard deviation versus a bigger standard deviation?
Small standard deviation, wouldn't that just mean that the spread of data is less?
Yeah, less spread. So I guess if we compare it to something like this, for instance, are we talking more like which one of these has a smaller standard deviation, red or blue?
Red.
Yeah, red's correct. It's a lot more narrow. It's a lot more condensed into the same set of x values. Sweet. So yeah, that's all. That's about conceptually speaking. This is a bit more conceptual as well, but it's literally just saying, which of these do you think looks like a bell curve? And I mean, there's arguments for a decent number of them. B could barely be one, maybe. C definitely. But yeah. This is what I was talking about, where the book kind of uses this a little bit. That's actually kind of funny. So they do actually start playing with it as if it was continuous. So they get your normal distribution. It's just another PDF, basically. So when you do E of x, well, now you're just doing x, f of x for this kind of thing. E of x squared times f of x in the CAS.
We're actually the same thing that we were doing last class.
Yeah, yeah.
Alright.
So at the beginning I said normal distribution is a subset of continuous, kind of like how binomial is a subset of discrete. All the rules of continuous also apply to the normal distribution. So if you, for whatever reason, preferred using these equations over the CAS stuff, then by all means you can play this entire thing with integrals. Oddly enough, you do get a slightly different answer. It happens all the way out like the 7th or 8th decimal place, somewhere far out, but there are actually slight nuances versus whether you use the CAS inbuilt functions for solving probabilities versus the actual rule itself. And so I'm imagining when they were creating their algorithms, probably for the inbuilt CAS ones, they, I think, would have cut some corners to speed things up. But it never matters because you never go beyond the 4th decimal place. Yeah, okay. This one kind of requires you to have remembered the equation. Actually, maybe I can show it up.
Is that because you got an x minus mean all over standard deviation?
Yeah, okay. Oh well, that's the z stuff. But oddly enough, that does actually appear in here as well. Yeah. So z being the x minus
Oh
mean.
yeah. It's gonna be 3 then for that one.
Yeah.
It's the fraction.
It's gonna be 3. Nice. And yeah, that is kind of cool, isn't it? There you go, your x minus mean over standard deviation. Or in other words, standard deviation was 1 and the mean was 0. So that disappears and there's no fraction anymore. You can see it's effectively transformations. You're replacing
Mhm.
that whole term with z. Yep, that's that. And then there's just a bunch of those versions again. What's e of x? E of x squared. What's the value? What's the value? They do a lot of those. Cool. And they do it as determining a sequence of transformations. That's kind of funny. Again, this is a book thing. I wouldn't worry too much about these, but if you're curious, I can have a stab at it. Brush up on transformation stuff if you're interested.
Yeah, sure.
Cool. Okay. So we're going from the take the graph of the probability density function of the standard normal to the normal. So we're starting at standard normal, which means mean zero, standard deviation of 1, and we want to get it to here. So we want to get it to the regular normal, which has a mean of 3 and a standard deviation of 2. What sequence of transformations would get us there?
Okay, dilation
Yeah.
of 2. Oh, can you say towards the x-axis? I don't think you can say that, right?
Towards that's yeah, that is kind of ambiguous to me. Usually use either along in the direction of or away from.
Yeah, it's not away from the x-axis.
Hmm.
So along the x-axis.
Yep. Dilate to along the x.
Or can you say that? Can you say like y-axis as well, or just x-axis?
Yes. So why do you bring that up?
Because I thought you could just say dilation factor of 2 from the y-axis
Oh, yes. Okay. No, I get what you mean. Yeah.
instead of saying along, because never heard that.
Yeah. So instead of saying along the x, you say from the y.
Yeah,
Yeah, precisely.
and well, translation of 3 units in the positive horizontal direction.
Yep. That's good. And a good order of those two. Making sure you do dilates then translates so the fraction doesn't mess things up.
Yes, always.
There is one thing that you touched on that I thought you were going to say that I had to clarify. There's one final transformation in that you haven't mentioned.
The standard deviation at the front.
Yeah, it's in 2 places.
So
Really cheeky.
that's gonna be 1/2 from the x-axis.
Half from the x. Yeah, precisely. That's what I thought you might be talking about when you're saying the y. So I wanted to clarify exactly what you meant. Yeah, so it's in 2 spots. You now have to say both of those dilation factors. And yeah, the good news is because this is X stuff and this is Y stuff, you can do those in whatever order you want. Whether you say the Y first and the X or the X first and the Y, they're
Yeah, I guess as
independent.
long as you say dilations first, it's okay.
Yeah, so as long as you do DRT, and even if you don't do DRT, you can still get around it with choosing your translations wisely. Like saying, for instance, what would this one be? This would be 3 over 2, because then when you multiply it by 2, yeah, that sounds about right. But yeah, this is just a bunch of that. And then this one here is the opposite. So you're going from these normal distributions to the standard normal, but it's all the same concept. If you got this, then I'm sure you get the rest of them just fine.
Yeah.
And especially considering it's not really exam accessible, I'll probably just leave those for you unless you're keen on revisiting that next time. Starting to get into some standard normal distribution stuff in here, and a bit of the approximate probability stuff. So in this one here, we have a mean of 100, standard deviation of 15. These are all basically the same question. We kind of already did this one in the notes, so we'll do below 85 this time. 1b, probability being below 85.
Is it gonna be 16%?
16%, probably. So what was that? 85 was 1 left. and then left of, yeah. Yeah, that's right. The other one was also 16%, which was one right. Cool, and then yeah, these are just going to be the same idea, but you're choosing, instead of 68% as the baseline, you're doing 99 and 95. We've done a bunch of these already. Similar stuff, but now you've got both an upper and a lower, or at least in this case you do, 3A.
%68%.
68% is good, yep. Nice. They're putting decimals in here. That's yeah, you could still probably be fine without the CAS. But rather than give you what the upper and lower is, they're actually telling you to solve it, but they're telling you it's 95% as the confidence interval. What would that make the ages?
Just 27 plus 6.2, so that'd be 33.5 on the upper round and 6.2, 21.1 on the lower round.
Yeah, chill. Awesome. I don't see this being any different now. Unless, where's the Z stuff? Yeah, question 10 starts getting into Z stuff. Let's do 10A on that one.
Valley. I want to say 50%, but I think that's right.
Yeah, so 50% isn't right, but you're on the right track. Why do you say 50%?
Like on the mean.
Yeah, it's directly on the mean. Yeah. Standardized value. Anytime you see the wording of standard or any permutation of that in a probability context, they're talking about the standard normal distribution x values, or z value, I guess in this case, because it's standard. So it's basically saying what is 160 in terms of z rather than x.
Can we go through this question on pen and paper and then like?
Yeah. So the easy way to do them always is using the z equation there. So to get from x to z, you're always doing the z equation, whether you're doing it in your head or otherwise. I'm just getting the iron out. Cool. So always starting with z equals x minus mean on standard deviation. What values do we already have?
The mean.
Yeah.
The standard deviation, and is it also that like is 160 centimeters tall like sort of the x value?
Correct. Yeah, it's the x. So whatever the thing you're told is the normal distribution of is x stuff. If they then refer to standardized or standard anything, that's when you're getting into z. And so yeah, the mean was 160, the x value was also 160. The standard deviation doesn't even matter here at this point, but it was 8. Z, therefore. Yeah. Another way to think about it, because z is effectively just a number of standard deviations, you can just treat it like you were doing before, which was, you're like, okay, cool, this is plus minus 2 standard deviations, so it's this probability. But instead of saying a probability here, you just say, oh, it was X number of standard deviations. Z number of standard deviations. This one, of course, being 0 standard deviations because it is the mean. This one, comparing 150 to 160, you'd say, well, it's a little bit more than 1. So it's going to be like 1.2-ish, whatever that fraction comes out to be. You'd have to actually probably calculate that one, unless you're good at doing... no, I guess it's just 10 divided by 8, isn't it? Or negative 10 divided by 8, because it's left.
Negative 1.25.
Yeah. And then 172, you'd be like, okay, cool. So add 8 again. So it's a little bit under 2 standard deviations, somewhere between that. You can do this sort of stuff in your head without needing a dedicated equation for it, but the equation's obviously nice to have.
Yeah, 1.5.
So yeah, if it asks you how many standard deviations away is something, or anything about standard deviations, they're effectively just telling you to find Z. That's just another way of phrasing that. Here's another. You've got some scores on math tests, mean, standard deviation, different person with different scores. This is a little bit different phrasing. Assuming both tests measure the same kind of ability, who has a better score given these distributions? So a mean of 78, but it comes with a score of 85, but it comes with a mean of that and a standard deviation of that, versus this one, which was a 27 score, but the mean was this and the standard deviation was this. Yeah, what do you think you do to go about that?
You want to compare the standard deviations, and then whichever one has more would have the better score, because they're further away from the mean.
Yeah, that's good. So it wasn't just comparing, this is a standard deviation of 6, this is a 5. It's more so, okay, how many 5s is this from the mean? How many 6s is this from the mean? Yeah, that's exactly what you're doing. You can do that if you want, but you've already got the point, it seems.
I'll do it just to make sure.
Yep, yeah.
5.78 on 5. And gonna be Cheryl. Cheryl has a bit.
Yeah, it looks good, because that's over 1 standard deviation. Yeah. Nice. 13 is just that, but a bunch. Oh, sorry, 14 is that, but a bunch of them. 13 is exactly the same.
Not so bad.
Yeah, no, it's not bad at all. None of these, I don't think any of the, yeah, only counting methods was one that takes a while to get used to. I don't think any of these different probability stuff that we look at Unit 3, 4, any individual ones are tough. It's just collectively getting through it when it's not chapter by
How do
chapter.
they make because I know like most schools, right? Because there's usually 3 SACs in a year for methods.
Yeah,
And
yeah.
usually like the probability unit is like really, really long. How do like schools stretch it out for so long if you have any knowledge of it? Like what do
How do
you
they stretch it out? Well, I think I might push back on 3 SACs. I think they do one for all of functions relations. They do one for calc up to diff. Some do an integration SAC and then probability. But yeah, usually probability is its own thing. Are you asking how?
like is it
I don't know if
anything
they.
else in probability that's like gonna be like crazy hard that they just spend so long on, or just like going in depth, I guess?
No, I mean, you've seen it all already. It goes up to chapter 17, and sampling and estimation, as far as I'm concerned, is literally just one new thing on top of binomial, because you just do one little conversion, and you're back to doing binomial stuff. I don't know. I don't think they do spend that long on it. I think they spend the appropriate amount of time, and then the rest of it's just exam revision afterwards.
Okay, I mean my school spends like a really long time on probability from what I've heard from the math
Really?
students. Yeah,
Okay.
we only have 3 SACs in the year. We have a diff SAC, and then integration, and then probability.
Oh, you don't even have a functions relations one at all.
I guess function relation, like
Yeah,
differentiation stack, just sort of like draws on your knowledge
yeah,
from
it's in diff.
functional relations and integration for that part. But yeah,
So what? You're gonna have a sack in. You're gonna have two sacks in unit in term 3, and then maybe all three of them in term 3.
no, I think probably like probability stack happens like early 10 4, I think.
Yeah, okay. I was gonna say because term 4 is starting to push it. Early term
Most
4 would
subjects in
be.
my school don't really give much turnaround. Like some of the people had like a sack like what 2 weeks before their final exam.
Oh no!
Yeah, not bad.
Oh, that's crazy.
This year's like really tight with everything.
Mm. Yeah, no kidding. All right. Well, good on you for now having all the content ahead of time, so you don't have to worry about their timeline anymore. I mean, yes, you have to do the sacks, obviously, but you're kind of already studying exam stuff while doing it anyway. So, yeah, that's that's something. Anyway, so that was some of the fundamentals there. This is where they get into the CAS related stuff. So whether we're using normal CDF, normal PDF, normal CDF and inverse normal. Yeah, play I guess a bit with that, and whether it's Z or whether it's X. Looks like doing a lot of Z here. Yeah, starting with a lot of Z anyway. This would just be playing with the CAS and knowing what does what. So we'll do at least 1A there, see how you go.
Okay, as is this going to be like 0.05?
0.05. Let me just double check the answer here. I think they've got it wrong in the answer. Because this is in fact Z less than. Oh, sorry, Z less than 2, not negative 2. No,
Ooh,
they did
okay.
have it right.
Then 0.95?
Okay, so you're probably doing approximate probabilities there. If it says, now actually that's a good point. How do you know whether using the CAS or whether using an approximation? Let's see. Approximate. Expect what percentage lie. Yeah, I guess in the actual exam it'll be obvious because you're in a tech-free or a tech-active exam. You just have the calculator or you don't. If you have the calculator, you always normal CDF. If you don't, you have to only use the approximation. The context of this chapter is teaching you how to do things with the CAS, so they're expecting you to use the CAS. It's less of a wording thing. They're all worded pretty much the same. It's just whether or not you're expected to have a CAS on hand or not.
So they want us to have to use a CAS.
Yeah, correct. Which
Yeah.
will become slightly different.
Round to two decimal places or
Yeah, whatever rounding.
0.98?
Yeah, 0.98 is good. Cool. That's just, testing how to use the CDF.
And if it's like equal, then does that make a difference or?
No. So same thing with CDF, right? Same thing with the integrals for continuous. In fact, yeah, I'll throw that back to you. Why do you think there's no difference?
I'm honestly not too sure.
Not too sure. Well, the hint there was the integrals. When it comes to integration,
All right, there's no like inclusive or exclusive bounds. It's just
yeah,
where you draw it.
yeah,
No.
there's no way to, or whether you include or exclude doesn't actually change the value because you're doing infinitely small slices of the area bit by bit. So yeah, it goes back to just the fact that underlying all of this, what you're technically doing is solving integrals.
Fizz.
Yeah, so the only thing to watch out for there would be, I guess, just reading it properly. This was not -2, but +2, but these are very easy things to...
You know, first I put into the CAS, right, and I got 0.98, but then I was like looking at it and I was like,
Oh,
standard deviations, and I'm like, it's in the 95% confidence.
yeah,
Then, no.
understood. Yeah, I get you. Yeah, so there's the negatives over here for Z stuff. They obviously get a bit wild with it, but if it's CAS, you just don't care. You just plug in what they give you. This is them talking about how it's not exactly the same. So 68% is an approximation, not exactly what you get for each of these. Okay, question 5. I'm not even going to say anything for this one, actually.
It's a standard and normal random variable from the diagram. Is it 1.28?
1.28. Yeah, that's it. Nice. Yeah, probably would have done the inverse normal there, putting in 0.9 as the value.
Yes.
Yeah, you're going to say?
Yeah, that's what I did.
Yeah, nice. Yeah, and because it's Z, mean 0, standard deviation 1.
Is there any sort of context I could put this in a like tech free or no?
I mean, when we did this sort of stuff, there was no CAS required here. You could use CAS, I guess, but you wouldn't need to. This is where you're doing the flips, comparing X to Z. Maybe we'll touch on that one next then.
You know in Stash, right?
Yeah,
I'll let if like you know when you find the gradient, like the angle between like two lines,
sure. Yeah.
like two straight lines. We
Mm.
learned like this thing that may I thought maybe it'd be helpful for methods is like I think it was something like so M2 minus M1
Mm.
over 1 minus M2 like times M1.
Mm.
And like that like gives you the gradient for the line that's like that gives you sorry the angle for
The tan
the
inverse
angle.
of that, or just the fraction?
Yeah, sorry, the tan inverse of that. My
Yeah.
bad.
Yeah. Okay. Yeah. Okay. So what are you actually doing by doing that fraction then? Because if that gives you the angle between those, then that fraction would be doing something to the effect of finding the line that would go. What are we
They
doing?
didn't really teach us. I mean, there was like this really long way of solving it, but
Hmm.
I like put on some like YouTube video of some Indian guy like trying to teach it.
Hmm.
And it's
Khan Academy
guy
or
no, it was just some like some random dude with like YouTube channel. Like
yeah.
you know the physics, like the guys that like the physics channels and stuff. And since I can like sort of understand Hindi, so I could like understand what he's saying.
Hmm.
And
Yeah. Okay. So it's like if you're trying to find. Well, hang on. So you got the theta here. What if you're trying to find alpha there? Because those are still. So which one does that equation actually give you?
it's like the acute, I think.
Gives you the acute. Okay, so you just do 180 minus to get your other one. Yeah, cool. Okay. Neat. Yeah, okay. Because otherwise you'd have to find like this angle here, and then you want this angle here, and then flip them.
Yeah,
Like
it's
a little
geometry
dotted.
involved.
Yeah, you'll be playing a lot with that, which is kind of what you do in methods. You have to sort of play with that a bit. Yeah, I have seen a question like this in an exam actually, where they asked for one of these. I think it was in one of our tech actives that we did, and I don't know if it was we want to adjust the angle here, but there was something like finding the range of possible values this could be. So I could imagine having your equation there would be nice to have because you can just get M1 in terms of M2 and then graph it, kind of like how you do applications of polynomials, where you have like your length times width, and then you get it in terms of just width or whatever the variable is, and then you plot it like that. Same thing here, but you're getting rid of the M1 or the M2. I could imagine something like that being nice. Oh,
Yeah,
cool. What was that equation again?
I think it was M2 minus M1 all over 1 minus M2 M1.
Hmm. And that gives you theta.
Oh, tan inverse of that,
Oh,
obviously.
yes, right.
I keep on forgetting that. I just keep on remembering those variables.
Hmm. No, that's good. Cool. I'd be curious to see a proof of that. I imagine it's doing all the heavy lifting of what you would be doing by hand and then just sort of putting the result in at the end. Something like that. Oh, cool. Nice. But okay, that's that. Where was the... Nah, those are the easy ones where you're just
Like,
saying...
yeah, I finally got it. It's like
Mm.
the tan theta is equal to the absolute value of that, like, of that fraction.
Ah, absolute of
When you,
this.
when you, when you transpose it, like,
Wait, sorry, absolute when you transpose it?
no, like, so then when, like, because tan theta is equal to the absolute value of that. So then when you, like, like, you can get theta to equal tan inverse of absolute fraction.
Oh, yeah. Oh,
The
right.
original
So,
tan theta is equal
inverse.
to,
Yeah,
yeah.
yeah. Yeah. No, fair enough. Yeah, because you'd want, yeah, why can you not have a negative there?
No, I don't think so.
Yeah, all right, because if you have a negative, you get this angle under here.
Yeah, yeah.
Oh, sorry, it wouldn't be. No, would it be? It would be, no, this sort of thing. That continued on, it'd be this. I think so. Anyway, no, that's cool. So, what are you doing in Spesh other than, so I guess you're playing with geometry?
It was just like, well, the first few lessons was algebra manipulation of like,
Hmm.
it was
What
like a lot.
textbook are you using for Spesh?
I'm honestly not sure. The teacher was just like showing it off PowerPoints, but I'm guessing it's gonna be Cambridge because that's what the school uses for most subjects,
Yeah,
math
okay.
subjects.
Let me see. Unit 1, 2, Spesh. See what you're in for. None of those seem about right. Yeah. You'll these proof chapters you'll love to hate.
Yeah, I've heard they're not very fun.
These are these are kind of special. I taught Spesh for one of my students just because I like, hey, I'm doing Spesh as well. Can you try and help with that? And I mean, we got by, but I was not qualified for it. I was learning these right before the class every time.
You remember when I was like, when I called you for before I was gonna join you, were like telling me that like you also taught one person special.
Oh yeah, same story. All these years, year later. Yeah, oh god, all this stuff. Yeah, I don't miss that. Find an actual specialist in that, because I'll just be learning it the same as you. Get back into matrices.
Did you find it like really hard or like it's attainable?
I mean, look, I've done this stuff before. It's just I don't have anywhere near the experience of teaching it, and I have to relearn it.
Like
Some
going
of the
from
stuff.
like to special, like how big do you think the jump is?
Say that question. Sorry.
going from methods to specialist, how large do you think the jump is?
I mean, it depends on your prior skill set. If you're just typical student doing it at the natural pace, um, I didn't do Spesh in school. I did it in uni in the first semester.
Right.
And you don't do all of this stuff. Some of the stuff I'm looking at here, like locus, kind of locus, we did a bit of that. Parametrics, these sorts of things we didn't really touch on that much. Proofs as well. So it was kind of like Specialite in the first year of uni, and that after having done methods wasn't bad. Like I did decent. I liked math. I could imagine if you're doing it concurrently with methods, the two people I know who did do Spesh were just like, we're not even bothering with methods because we're already learning it already in Spesh and we're just sort of grinding out Spesh.
Yeah.
So from what I gather, they were expressing it as if it was quite a big jump, but I didn't have any personal experience on that.
Yeah. I mean, so what I sort of like alluding to is like, what I find with methods is if I put the work in, right, I usually find it not too hard to like gather concepts. Like
Hmm.
in less than a year, like I feel like I've learned like a decent amount just
Yeah,
by going up to class and like taking some time outside of class to look at concepts.
well, that's
But
good. Yeah, because I imagine you've actually kind of got a similar experience to me then, because you effectively learnt methods before Spesh, because we did this whole thing before you've actually got into real Spesh classes. So you would
yeah,
have had a similar experience than I to what I did getting into uni, just in terms of like the natural progression of your skill set.
yeah.
So yeah, it makes sense then.
Well, let's see.
Do you already have this textbook, by the way? I can.
Yeah, I have like the
Oh, you
online
do. Yeah,
PDF.
okay. I was going to chuck in a copy if you didn't already have it. Maybe the 3.4 one. Do you have the 3.4?
Honestly, I'm sure I could probably just like find it from some website.
Sure. Yeah, I mean they're everywhere. The main one that I pulled all my stuff went down. The ATAR rocks or the like it went down
Oh,
down forever.
yeah, there's a new one.
VCE
Uh,
best.
yeah, something like that. It's
That's
just
also dead.
I guess whenever they get onto them, there's like a new one. I remember my friends talking about a new one just a few
Yeah.
days ago.
If you find like a new one, let me know because I need it.
Oh yeah, okay,
um,
yeah,
but yeah, the two that I know of are both dead.
yeah. I'll say I remember my friend talking about it. I'll send it to you if I can find it still working.
Easy. If not, I still have a copy of the 3.4, so I can give you that for Spesh.
Yeah, no worries.
Cool. All right, that's about it.
Yeah,
I'll
thank you.
leave you to it. Take
See
care.
ya.